So let's discuss decoding in detail. What do I mean by decoding? And we have I think heard, you might have heard of decoding word in previous lectures, and we had kind of discussed this a bit. But just to kind of formalize it and discuss this in detail, we need to discuss decoding in NLG. So here is the model what you see in this diagram. So what is the task here? The task here is NMT, which is neural machine translation, and this model is called encoder decoder model, or you can also call sequence to sequence model. So why do we call it sequence to sequence? Because at the input we have a sequence, and at the output also we are generating a sequence. So that's why it is called sequence to sequence model. Also some people call it seq to seq model. So why do we care about seq to seq model? Because seq to seq models are super famous for not just neural machine translation, but many other tasks also can be done using seq to seq model. So you can encode your text at the encoder module, and you need to decode the text at the decoder module. So decoding, in very simplistic terms, it's just generating. So generating is decoding. And how do we go about it? So given this sentence in French, and which is he hit me with a pie in French, and we need to generate the English translation for it. So how do we go about it? We have an encoder RNN, could be LSTM, could be a bidirectional LSTM, could be simple vanilla RNN, could be GRUs, and so on. Then what do? We pass each of the input text, not just the word itself, but some representation of it, some embedding of it. So maybe these embeddings are coming from word to vec, or it can be also one hot, or maybe it can be just d-dimensional randomly initialized vector. So you have these representation of these input words going inside the RNN one by one at each time step. So when this IL will go to the RNN, you will generate the hidden state, and then this will be passed to the next, and then you will feed the next word, representation of the next word, and it will generate the hidden state 2, and so on. And at the end, the last hidden state you will get when the entire will be feeded in. Then you will get the last hidden states, and this last hidden state will be utilized by another RNN module, which we call decoder RNN, and this will take the previous hidden state as the output of the RNN encoder, the last hidden state, and then let's say with the start representation will go in, and then what you do, you calculate the y hat. How do we do it? So what you get here, the logits, and then on logits you will apply the softmax. And when you apply the softmax, it will give you the probability distribution over your vocab. So let's say you have vocab, let's say the size of the vocab is 10,000. So you will get 10,000 probabilities from here, and then you need to apply the argmax. So that means that from these you will have to select the word having the highest probability, and then let's say it was he, so you will generate he. So you will say that the decoder has generated he, and then what will happen, this he will be feeded back to the decoder RNN, and what you will generate the next word. So you will get the hidden representation from here, you will get the input previous generated word he as input here, and then you will again you will apply the softmax, you will get the probability distribution over your vocab, and let's say this time hit was selected as the maximum probability word, or max probable word, and that, and so on. You will have to do the same thing again and again until unless you generate the end token. So you will start with the start token and you will generate the end token, and once the model generates the end token, you can seize the generation, or you can seize the inference. So this setup altogether, what we are talking about here, is called student forcing setup. So why do we call it student forcing? Because here we are, the current word we are generating in the future time step or the next time step, we are utilizing the same word generated and feeding back to the decoder RNN, and this setup is called student forcing. And what we do here, we are generating that as not, it's not training, it's inference, or it is at the test time what we are doing. So once the model is trained, we'll have to test it, or maybe the model is already deployed. At the inference time, we need to generate the text, and it's a NMT model, neural machine translation model. So for newer sentences which are not part of the training set, we will be generating the translations, right? So how do we calculate the probability for generation? So let's say given the sequence X, let's say this whole sentence is X, and we need to generate a translation Y. And how do we compute this probability? This probability we will compute that given the X, given all these as this hidden state H4, we need to generate the first word, we have generated the he. Then what is the probability of Y2, which is the hit, given Y1 is already generated and also X was provided. So what this formula says in very simple terms, that the probability of the current word will be the probability of the generating this particular current word, let's say Y4 will be given Y1, Y2 and Y3 are already generated. So we'll have to consider all the already generated words when you are computing the probability for the current generation of the word or decoding the current word. So, and one more thing we missed to discuss here, that this is a conditional language model. So this is a setup of language model we have already seen. When you predict the next word, then it's a language model. But it's not a normal language model what we had seen, let's say in TAG-LM and so on. It is a conditioned language model where it is conditioned on the input text. So you need to predict the next word, but you need to have this X also. So you know that X is given as condition. So this is called conditional language model. And why it makes sense to have it, why it need to have this encoder, decoder, or seek to seek kind of architecture to do NMT and some of the other tasks, or maybe even story generation. So you're giving the your premise or some of the instruction, what kind of story you want to generate here, and then this will go into the encoder RNN, and then at the decoder RNN you will be generating this story. So why it is sequence to sequence or end to end model? This is called also end to end, because this works as a whole. Even though there are two RNNs, maybe two LSTMs or bidirectional LSTMs, or not just that, it could be also layer of multiple LSTMs, a stack of LSTMs. But at the end of the day, when you are training, it works, it behaves like a single module. So when you compute the loss, the gradients will flow from the decoder to encoder also. So when you are computing the gradients, and when you are doing the step in SGD, stochastic gradient descent, then weights of this RNN or this LSTM will also be updated apart from the decoder weights. So that's why it is called end to end. so behaves like a single system. And what we are doing here, so this is the training time. So at the training time, what is the difference? So what we had seen previously was the test time or the inference time. Here we are training the same system. So let's say now this example is part of my training set. So it says the same thing, he hit me with a pie in French, and then you need to generate the English translation. So now again, in very similar fashion, your each of the word and the embedding of the word will go inside or feed it to the RNN1 or encoder RNN, and one by one. And then at the end, let's say this H4 got generated, this hidden state 4 or last hidden state, and then it will be passed to the decoder RNN. Now the difference comes into picture. So here in the inference time, what we were doing, we were also feeding start, that is same, and let's say we generated he here. And how do we generate it? We know the answer, so we know what should be here, and let's say it generated something else, then we need to compute the cross entropy loss, and let's say we get this loss here, and similarly, and then in the next step, rather than using he and feeding back to here of the generated he, we already know the answer before, so we will feed from the training set itself. So we know this sentence from the training set, so we are not sending the generated text, generated word here, but we are feeding already known labels from the corpus itself. So let's say rather than generating he, it generated, for an example, the. So we are not feeding the here, but we are feeding he, which is the original true word that should have been generated. So this setup is called teacher forcing. So now you know there are two kind of setup. One is called student forcing, where the generated word is going and feeded back to the decoder RNN at each future step. But in case of teacher forcing, we already know the labels or true words, and we feed those words rather than newly generated words. So that's called teacher forcing. And then we complete the whole sequence, and then we generate these losses at each step. And then the final loss we have already seen when we were going through RNN, that will be the average of the all losses, and this will be final loss for us. So in terms of decoding, what we had already seen, what we were doing, uh, what we had seen so far, that given when we want to generate a text, generate a word, let's say this is the decoder step 1, we are getting something from uh, encoder hidden state, maybe it is the last hidden state ht, and that goes in, and then you need to generate the first word, and start also goes as an input. You need to generate the first word. So what you need to do, the score or the value, what you logits you will get here, you need to apply the softmax. You will get the probability distribution, and from this probability distribution we will take the max value. Let's say it is here somewhere. So you get the max, argmax, and you get the value as he, and you get the word as the maximum probability word as he. So that is what we have already seen, and this strategy is called greedy decoding. So that's what is happening here. So having let's have it in more formal way. So let's say this yt you have generated, and this model generates the score for this yt, So this goes in and then it generates the score for this yt. You apply the softmax function on top of it. So this is the softmax function. You get the probability distribution over your vocab, and after getting this probability distribution, you will have to apply again a function g, which will give you the predicted word as output. And in case of greedy decoding, what we have already seen, this g function will be just argmax, which is selecting the maximum probability. So this, what we had seen, this is called greedy decoding. And one information which is left, and there is a term called auto regressive. You might have heard, some of you might have heard of it. So this auto regressive fashion or auto regressive decoding, you can call it, is the simple, very simply, this is just the feeding back the already generated word every time. So this is called auto regressiveness. So auto regressive feedback. So this is we call auto regressive feedback. So what we have seen, at each time step when we are generating these words, we are taking the most probable word as the output or the answer. So there is a problem with this, and the problem with this is, if let's say this was the same example what we had already seen, he hit me with a pie and the model generated he with the greedy decoding. So maximum probability at the first time was for he, then model again generated hit which was having maximum probability, and then model had to generate me. Rather than generating me, it generated a. So let's say model generate a got the maximum probability. Then the problem is model cannot backtrack or cannot go back. So we'll be left with the wrong translation now. So it will be he hit a, and then what to generate. So it's a wrong translation. So model cannot go back. So that's why greedy decoding is problematic. Then how can we fix it? So what we can do, rather than generating maximum probable word or having word having maximum probability, what we can do, we can search for a word from the probability distribution. So let's say this probability distribution is there. Rather than selecting just this max word all the time, we can select something which is more appropriate. Let's say it lies here or maybe here. But how to go about it? So to do that, and with this very familiar equation which we had already seen in previous slides. So what we can do, that at each step t of the decoder, we can have v raised to the power t possibilities, partial translations, and then v is the vocab size. So what it says, that let's say we generated he already, and then he, and next true word is hit. So rather than generating something which is coming from argmax, we have v possibilities to fill this in again. So we need to do exhaustive search to come up with v possibilities, and not just v possibilities, but we need to satisfy this algorithm where this probability needs to be maximized, and for each of these cases that needs to be maximized, then it should be v times t. So it will come out to be vt. So moving on, we have already seen that greedy decoding doesn't work, and all this exhaustive decoding will be too expensive to calculate all these combinations, and running for each combination. So the authors propose, or some of the researchers, they have proposed beam search as an alternative. And what do we mean by beam search? So this aims at finding the strings that maximizes the log probability, and with wider exploration of candidates. So it also kind of tries to maximize the probability, the expression we have already seen, but we need to have more candidates for that.